Welcome. Nice to see you all. The latest session on this day. I'm looking at a lot of tired faces. I hope I can put a smile on your face, beside the fact that this is actually, it's not such an easygoing topic, right? It's from its mathematical and scientific perspective, it's hard to understand. On the other side, it has to do with one of the baddest periods of our humankind, the Second World War. But to me, it is a super interesting topic. So I want to tell you something about the Enigma. And due to the fact that this is the PowerShell conference, I have to implement it in nowadays technology and PowerShell, of course. My name is Thorsten Butz. And as you already heard from my accents, I'm from Germany. So I'm a little bit in the center of the topic, right? Because I was not on this planet when the Second World War was, but of course it influenced my life. Things I learned on school and all these things. But before we start with that, let's just once again thank you, because I think you are the most important people here. You are my favorite sponsors, and of course, all the companies that support us. Thank you for that. I take pride in training people in PowerShell. That is simply because I like it. I'm actually not, I tell it often, I'm not that technical, nerdy guy. I never was. But I really like to explain things to people. And of course, I have to understand the technique. It will not work in other ways. But I always think about what is a good metaphor? What is a good example? And what I personally really, really like is that the main idea to me in PowerShell is simplicity. So, and we will talk about that in just a few seconds. You might have heard that I also run a podcast which deserves the name Slowcast, because I create maybe once or twice a year a new episode, because I can't find the time. But on the other hand, I think it's worth listening to it even a few years later, and I got a lot of people from the PowerShell team, and to me, it's a little bit of kind of documentary, a little bit of living history, if I reveal my session with Bruce Piet, for example, Jeffrey Snow. You might have interest in that, besides the fact that it's named Sliding Windows DE. In many cases, it's in English, because some of my guests don't speak German. I don't know why. So you will find out. Why I'm here? I love mugs, and I can't stand to collect more and more. It was a little bit unfair when Rob asked on day one who was at 1, 2, 3, 4, 5 PSConf, because I was thinking about how many had we. So, and I wish I had that slide, because I was to all PSConfs, that modern style that were in Hanover previously, last year in Vienna, but there were more even before that. But this is the reason why I always show the mugs, and I hope I get a few more. Let's see. What's my motivation to talk about Enigma? There are three things that I would like to mention. The one I already mentioned is I'm from Germany, so it touches me. Of course it does. The second thing is I work in the IT space, so we all know the name Alan Turing. And as you will see later on, I hope I find enough time to really honor these people around, and of course, Alan Turing also. Working in the IT means you know Alan Turing as one of the great scientists of our lifetime. Or not in my lifetime, he was dead back then, but in my century, let me say it like that. But honestly, the motivation for this very talk was the third thing, and that is very technical, because that's the reason why you're here, maybe. Do you know these statistics where you learn what is the most beloved programming language? So never trust a statistic that you didn't create yourself, but people say JavaScript is quite popular, and Python. And PowerShell, I think it needs a little bit more love, right? So When I talk about PowerShell, I often wonder why do people prefer, for example, Python? And if I want to compare something, I would personally compare Python and PowerShell because they are, in many cases, in many aspects, they are very much alike. And one day I stumbled across a number of implementations of the Enigma code in Python. And I found out, at least from what I Googled, there are so many implementations in almost any programming language, and there are tons of implementations in Python, believe me. Some are good, some may need a little bit improvement from what I found out. But I found not a single implementation in PowerShell. I thought, that needs to be done. And the interesting thing to me was, I didn't start from scratch. I intentionally took a number of implementations in Python and I translated it. Because, and this is the reason why you see Snoopy here, it's pretty interesting to me to see how languages that are very good comparable, how they differ in some aspects. And if you try to stick to the philosophy of the Prestine version that you follow, in this case in a Python implementation, then you do things differently. For example, there is a huge discussion about classes in PowerShell. Do we really need it? In many other programming languages, it's absolutely natural that you use classes all the time. In PowerShell, you can discuss that. Some people love it. Some people think they are not necessary. So I took the chance and actually intentionally created it just the way you will see it now, using classes, and you will have to find out if you like that kind of code, or if you would go a totally other path. And this is what me interested, to show my students, for example, or if I write books to compare these things, what are the different ways to do the same thing? You will see that in a second. So that is the reason why, if you compare, this is a class in Python, and this is a class in PowerShell, right? It's very comparable if you just focus on this one thing. But let's start from scratch. I think everybody heard Enigma, but only few people really understood what it does, because most of the time you hear about the process of cracking and decrypting the Enigma messages. Let's talk about that, but let's talk about the basic principles. The basic idea of Enigma, when it was founded in the early 20th century, when it was invented, the basic idea is a one-time pad. And the fun thing about a one-time pad is that it delivers perfect security. From a scientific perspective, it can be absolutely secure. And why is that? Because the main idea of a one-time pad, if you want to decrypt one letter, it is very simple to understand. For just one letter, you need a whole alphabet, and you just compare the letter that you want to decrypt with the alphabet. And of course, the alphabet is scrambled. So in this case, as a very pretty example, if you want to write down ABC, and you look at the red items here below, it would be GLE. But that would be a fault, because the second that I decrypt the first letter, I have to throw away the pad. That is the secret. For every letter, you have to use a new alphabet. And the alphabet, the scrambled alphabet, must be totally random. And as you might already think, some things went wrong with the Enigma, because it would have been way, way better, and it would have been a problem to decrypt it at all if Nazi Germany wouldn't have a lot of faults in that. So, but later on. So if we think about that, how would you implement that in your favorite programming language? Of course, you would think about ASCII numbers, and let's limit it to only the capital letters from A to Z. No umlauts, no numbers, no special characters, nothing. And the fun thing is that is exactly what the Enigma does. The Enigma knows only letters. So capital letters. But actually, it doesn't mean anything. It could be also minor letters. But anyone describe them as capital letters because this is what you see on the type when you type it in. So in this case, I think you know that in the ASCII alphabet, the letter A is encoded as 65, character 65. So that again would mean that you replace the first letter with the equivalent in the red line, so 65. So let's find out, how does that look in code? I tried to create this in code, and as you can see, I use Jupyter Notebooks here to make it a little bit more easy to follow along. And again, you have that 2 alphabets. And the very start of it is simply what you see here. You simply decode letters as numbers, because it's very easy to calculate with numbers, of course. So if you think about that again, you're not interested in the characters from 0 to 64, so you have a certain offset that you see here. And if you now want to create a one-time pad, so a scrambled alphabet, the only thing you have to do is this. Wait a second. This is what creates an array of random letters from A to Z. That's what it is. So let's find out how that works. And you have to take care for this. This here, this is the alphabet, right? So, and with a modern computer, it's pretty easy because I can create such scrambled alphabets all the time. That is not a problem. The real problem is to get them random. You know, from a scientific approach, it's super hard to create random things. So where do they come from, right? So, but what you also see is the letter A that I hear and try to encode must be a capital letter so that it makes sense. So I created a regular expression, of course, to check that. So if you put that in a function, and you should really take care here because this is the part that you actually can understand easily. I assume it will change in a few minutes because the code is getting longer and longer. It's hard to follow, but you don't need to understand it today. You need to understand the basic concept so that you can download the module and try that on your own. Maybe you find interested in that. So if I have something like here, encrypt the letter, and you have to find out here in a Jupyter Notebook, you see the output below the box, and you see that I got the letter C. If I repeat that, I got anything. Maybe a letter C, maybe an X, maybe something. And I could also get an A. This is important. Of course, in one of 26 cases, it should be an A, right? If it is equally shared. Yeah, you have a question, Maximilian. Yeah. Yeah, the question was, is the one-time pad, does it create unique results? So every letter can be in that alphabet one time? Yes, it will. It should be, it must be. You can see that here. That should be every letter of the alphabet, right? Over there. One more question. Yeah, maybe it's a little bit, he mentions that encrypt, decrypt is sometimes a little bit hard to understand. The fun thing in one-time pad is that the way you go in, you can go out, right? It is synchronous, if you like that. So that is the basic idea. And of course, we don't want to create a single letter. We want to create a whole text message. And the final example here is, of course, I would create a commandlet with that basic idea. So let's find out what that is. And I will try to encrypt here the word weather forecast. If you translate that to German, this is a word, Wettervorhersage, which was very, very often used by the Deutsche Wehrmacht, the army in World War II. And this was one of the main of the main ideas. How can we break into the enigma? Because we simply think about what will they send. And if we know that they send a Wetterbericht, a weather forecast every day, we have something we can try. So that is the reason why I chose the word weather forecast. Of course, in World War II, it would have been German, of course. So let's find out what happens here. If I click here, you see what happens. You have all the one-time pads, and every single letter is decrypted. And if you do that, fine, it's perfect. This perfectly fine. You can't decrypt it from what we know today. So that is the basic idea of the enigma. So, and if I repeat it here, wait a second. Of course, if I call it again now, the letters change. Let me just comment that out. So one more time. And then you see here, I got that weather forecast. Just wait a second. And now we want to see, wait a second, I was a little bit too fast. I first of all want to show you the encrypted message rate. And this would be like that. One more time. So, and now you see here, this is the encrypted version, and you don't see any Wettervorhersage any longer. But if I pipeline it, because this is what my commandlet allows, it will directly be unencrypted. So I hope this is understandable. Try that on your own. So, and you see, if I pipe it, first I encrypt, then I decrypt that again. Then again, I have weather forecast. But the interesting part is to see this in between, that step in between. So that is the basic idea of the enigma. But the problem is that back in those days, they didn't have any computer. The enigma was created in the early 20th century by a German guy, not a military guy, Arthur Scherbius. He died just before the war even started. The enigma itself was a fine idea. It was a very, very good cryptographic device. But you can imagine it's a little bit hard to build these elements because this is a mechanical machine. You need some power, because I will explain that in detail in just a few seconds. You need power simply because the encrypted letters light up, because that was the easiest way. But the machine itself is totally mechanical. So you just need a small power supply to see the encrypted messages, and of course the way it works to close the circuits that made the encrypted letters shine. First of all, the military wasn't interested. In the 1920s, a lot of these machines were built, different variants. I focus here on the today most beloved version. Let me say it like that, because you find this machine all over the places. Every picture that you see, I took it myself in Bletchley Park, most of them. That's my final part of the talk. These machines were built in a huge numbers, maybe a few 100,000. Nobody knows exactly, but they are lost, of course. But we have quite a few. Mankind has quite a few in the one or the other museum, so you can work on these items, explain it to people, and there are a number of videos. You will find them on the portals. Where people explain that, maybe on an original Enigma machine. And in most cases, it's just this version with the 3 rotors. There are differences. I'll tell you later on. And just because, this is why it's important, just because it was a commercial machine, anyone could buy it. Lots of people bought it, and some mathematic scientists from Poland, they were a bit skeptic about their neighbor, and they bought one of them, and they started to think about, can this encryption be broken. And the group, which Marian Rejewski was one of these scientists, was pretty successful. And when Germany started the war on Poland, first in 1939, they took the chance to flee out of their country, and they gave everything they had, their knowledge and things that they built, to the British military. So that is the reason why people like Alan Turing, Gordon Welchman, and many thousands of people in Bletchley Park later on, they didn't start from scratch. The famous Turing bombs were also invented by the Polish scientists. So that was just, they took the idea and brought it to the next level. You have to understand how it works, at least the basic things. So what is important if you want to write that as code is the operator has to type in what he or she, in these times it were a man, what he or she wants to decrypt letter by letter, and now you see it is just the capital letters, nothing else. No special characters, no numbers. If you wanted to write down 8, you have to write down the letters. And how that worked, I will show you. I will demonstrate that, how they did it. That was quite special. And the first thing that happened is, when they typed in a letter, it was for the first time scrambled here below in the so-called plugboard. That wasn't available in the very, very early years. It was invented a little bit later. So it could happen that the letter A, for example, is directly scrambled to anything else, because these plugs are a direct connection from one letter to the other. For whatever reason, nobody knows, the Nazis later on decided that they will use 10 pair of these plugs, so 20 letters from these 26 were scrambled and 6 were not scrambled. But it makes it more difficult, of course, to break into the code. That is the first step. You will see that in the code later on. And the second step, and now that we're back to the one-time pad, are these rotors here above, what in Germany is called Walze. You will see we have 3 of them. And I highlighted a little bit more. And actually what happens when you type in, you try to close a power circuit so that at the end a light will flash with the encrypted letter. And it goes through all these different steps. And the first step is the plugboard. The second step is the entry to this set of rotors from right to left. And to make it a little bit easier to understand, I go in there. And now you have here the typical, this is the fast rotor. It is called fast because it moves while you type in letters, it moves any time you type in, and it moves. And the second one, the one in the middle, moves from time to time. And the third one doesn't move at all, really, in most cases. So you go from rotor 1 to rotor 2 to rotor 3, from right to left. And then something very special happens. You see the letter B here. This is important. This is the so-called, oops, that was wrong. I want this. This is the so-called reflector, in German Umkehrwalze, UKW. If you read UKW in the documents, then it is this reflector. This is actually nothing else than another rotor, but you can't move it. Because, and now it's getting important, the main 3 rotors here in the middle, you can move. And you can move it in 2 aspects. The first thing is you see that it is kind of wheel here with some kind of notch, and you can push it forward, of course, so that you have an initial setting that is totally different from what you did before. But that is only one thing. Internally, you can't see that good on this picture because the rotors are in. Internally, they have another wheel you can also turn around. So that gives a huge amount of possibilities for an initial setting. And the fun thing is, I told you about one-time pad, that it needs to change every time. This is done by typing in a letter, and anytime you type in a letter, one of the rotors moves one step further. And from time to time, you can compare that with your mileage in your car. When you go 1, 2, 3, 4, 5, 9 kilometers, then the display, back in those days when it was mechanical, it pushed the second item, you know what I mean? And then you come to 1, 0, what we call 10, and this is the same principle here. So you have some notches that from time to time you push it forward. So, but one of the weaknesses is the people that built the Enigma, they thought it is super great. We have so much more permutations if we go from right to left and then back from left to right. But what they didn't think about, or they didn't thought about that enough, when you do it like this, then you have the problem that you must not get a short circuit. So the problem is that in this Enigma, the final output can never be the same letter that you type in. It can be anything, but not if you type in the letter A, it can't be A. And this is one of the main weaknesses that they attacked later on, because they knew less, but they only knew a few things, but they knew a letter A can never be encrypted into A. Yeah? And they did that because of the convenience. With the same initial setting that you will see in my code, you can simply encrypt and decrypt. It is absolutely the same. You go in, you go out. The way that you go in here is the same way that you go out when the session is over. So, one more thing. It is important to understand when you program that, when you develop a script for that, these rotors today are well known because they were manufactured in a high number, and there were certain models, just as when you buy shoes, yeah, with different sizes. But once you know how these rotors are manufactured, you have a list with specific settings that are possible. I will show you that in the script. Today, this is known. Back in World War II, it was a big secret, of course. That's the reason why when someone had an Enigma, for example, on a U-boat, on a submarine, they were forced to destroy these items before they do anything else. So, because it was very important to keep that secret as long as possible. But from nowadays perspective, it's very easy. You go into Wikipedia, everything is very well documented. You will see that. The Enigma, this model, there were 5 different rotors. So if you try to create a script, you know that there is a rotor number 1, rotor number 2, rotor number 3, and you can get the actual, the precise way that they were built on Wikipedia. So that is important. And how did that work in real life? That is the next step. How do people that are 1,000 kilometers away from each other, how do they know what is the configuration of the Enigma that the other one has, the sender has? That is, then I can explain that in a second. This is a big picture of the plugboard. If you look at the possibilities, if you do not care too much about some weaknesses, this is a very, very secure machine from its design. If you compare that in a key length that we use today, it would be 76 bits. And I put here for comparison that the DES, the data encryption standard that we used until lately, that is only 56-bit. So that's a very, from its basic design, it's a very, very secure machine. And now, this is the important part. If you focus on writing code with the Enigma, I think you have to learn German first, because everything is German, of course. And this is the one thing that is very, very important. This is a sheet of paper, and on the left-hand side, you see there are dates, datum, I think it is well readable for anyone. And it's just the date of a certain month, the 1st of the month, 1st of June maybe, the 2nd of June, etc., etc. And the operators of the Enigma, they had that sheet, and they had exactly, if you were on the, let's say, the 22nd, you just focus on this line. And then you know you have to pick up these rotors, you have to bring them in this setting, one column right, and you have to plug in these items here in the middle of the picture. And I know that this must be hard to read, so I did one thing. I tried to ease your life, and I recreated that in Excel, and I translated it to make it a little bit more easy to understand. But I also added one thing that is very important. Again, on the left-hand side, the date, the set of rotors, that is, which rotor do I pick? Everyone has everything has a number, and you have to pick this or that. And how do we scramble the rotor? What are the plugboard settings? And that's it. The indicator groups are not important in terms of decryption and encryption. So that is on the board. That is simply to let the recipient know if it is for him, for his division, or for anyone else. That is nothing else than a department, if you like. One thing that is missing on the original sheet here is the so-called reflector. That is another weakness. There were different reflectors. They manufactured it, but they didn't use it in many cases. So they, for whatever reasons, again, they all the time used, or in many cases, they used reflector number 2, which is called reflector B. And that, of course, limits the possibilities from today's point of view. So one more thing. This is important because this is what you need to know to work with my code. You have to understand only that, if I may say it like that. So let's start. I tried not to be too complicated because I know it's already late in the afternoon, but I want to highlight the basic items. First of all, you need to have some helper functions. I showed you that before as a one-time pad. You need to translate letters into numbers, so I create a little function, string to numeral. You need to have some code that rotates. This is what this does, and so on and so on. But the real magic happens, and the interesting part starts in the second block. So let me just execute that so that it is in memory, because I know I need that, of course. And now this is exactly what you will find on Wikipedia and in any other documentation. These are the initial settings of the rotors that were manufactured back there. And I put some more in for later use. In this model of the Enigma, they had 5. So 1, 2, 3, 4, 5 are fully enough. And keep in mind that the people in Bletchley Park or any other opponent of the Nazi Reich, they didn't knew that when the war started. These were the so-called reflectors. I mentioned that in most cases, the people only used a B for whatever reasons. And one more thing, very important, is this here. This is the notch that is important when you type in a number of letters. At some point, maybe first try, second try, or the 26th try, you will rotate the next item, you know? And this is the placement of the notches. So, and in these 5 rotors, there were only 1 notch. They could have made it better, creating multiple notches, of course, so that it could rotate way more often. And I created these items, as you can see, as just a string, because that is easy to handle. You can copy that from Wikipedia. That is the reason why I did. But to calculate with that, I need an array. So I took pride in creating array lists. It makes it a little bit easier with the add method. So, but you could also use a simple array. So we try that. So let's come to the classes. I created two classes, one for the rotors and one for one rotor and one for the Enigma itself. And you have to know that if you only focus on a single rotor, it is defined by which rotor is it from that set of 1 to 5. And the second thing is, where do I put it in? And in which initial position? That is what it defines, so I need 3 values, as you can see here. If we focus on the class here, later on you can judge yourself if you like it like that. As I told you before, classes are not so familiar within the PowerShell space as they are in other scripting languages, but I intentionally decided to do it just like this to make the code comparable with lots of other implementations in, for example, Python, as I told you. So you see that is a lot of code. It's really hard to handle. If you don't do it every day, it takes a lot of time to just think about it again and again and again. I hope it works now. And if I create this class now, we can check that out here below. It is just like that. I initiate the class with a certain setting. And then I have 2 methods to click when I type in a letter because it has to push forward. And the rotor must tell, is that a position where we find a notch? So that is the second item here. So let's just do it like this. That is the most simple way. And let's execute that. And now you see this is what my script code does. You see it here below. It looks a bit rubbish. But I created a lot of output to make it easier in terms of debugging. That is why you find in my code very often the word debugging. That's not because I debug all the time, but if I need a little bit more information, these items could also be removed, but it makes it easier to understand where the faults are. So to not be too long, I need to hurry up a little bit. The second thing is, I commented out. The second thing is the Enigma class, and that exactly represents what an operator does in the morning. Just imagine you're a soldier on a submarine. You would have a look at that cheat sheet, and then you would set up the Enigma just the way it is told over there. You get out the correct rotors, put it in the right size, you took all the plugins in, and you do that, and this is what is reflected here in that. And you see it's a lot of stuff that you need here. And I also provided some links. The Enigma has a certain kind of anomaly. It's also a little bit strange to implement. I put it here and I directly attached the Wikipedia article to make you understand what it is. Again, it's nice to speak German in this case because the German Wikipedia articles are very, very good. Way superior than the English one. So the Germans here in the house, I really recommend to read the German Wikipedia articles first. They are very, very detailed. The English are very good, but the Germans are a little bit more detailed. Yeah? It's a topic for us, of course it is. So again, I call the code so that it's in memory because we want to see what's happening now because we're finally approaching the end. Not the end of the session. I have a little bit more. I hope you have a few minutes left. But this is the function that actually translates the code. And you see, again, lots of code. Take a look at that. And, of course, I have to also run this to define the function. And let's see what happens if we use this now. When you try to use it, all you have to do is what is listed here, what you see now. You simply run the script so that it's in memory, and then you initiate a new Enigma, give it a variable name. This is the initial setting. In this case, we don't use the plugboard at all. And then you want to translate hello world. So let's find out what that is. If I run that, you see it here below. This is the code. And keep in mind, as long as you have the exact same setting, the code that you see must, in return, lead to the plain text message. So try that out. If I do it here below, you see it's exactly the same. Then you see hello world, right? This is what it's meant to be. And if we now take a real world example from what we had in that sheet, if I may allowed to say it like that, then you see again weather forecast, that is the German word, Wettervorhersage. And if I run it now, you see it works. But hopefully it works. So, and you see this, the first line is the encrypted message, and the second one is the decrypted message. So, but this doesn't mean anything, because my implementation could be totally broken as long as it is true or if it's correct in itself. The main problem is, did I actually wrote code that reflects the real enigmas? That is the main thing. So we have to do one more thing. We have to find a real message from World War II and have to decrypt it. And there are a lot of examples you can find out in the world. And you will see it is a little bit annoying to read that, because obviously it's German, what you see now, and it is really rubbish German. So, but you can check my code and you can see if my output is exactly the same that you see on any other simulator. It must be, right? It must be the same that you read in any book and stuff like that. And if you run it now here, you see this is the output of the message. So, as you might see, it is not really good readable. So that's the reason why, again, I made it a little bit easier, again, because the operators, they had a certain way to work. They put everything in 5 letter groups. Yeah? And for those of you who speak German, you do now have a chance to understand what here is. For example, the first letters are drei, the number 3 in German. So, but to make it a little bit easier to understand what's going on here, I go back to my PowerPoint slide and show you what's up here. This is exactly the same that we just saw before, a little bit more detailed. And this is what came out here. And what you need to understand is that this is not really well readable, right? I try to make it a little bit easier for you to read, because there are some tricks. They could not use any white spaces. So the operators have to replace white spaces with something. In many cases, they didn't, so they put one word after the other. And if they abbreviate the words, then you don't understand a single word. But because it was war and they knew what they talk about, they had an idea. What is the message of that encoded message? But anyhow, what they did is, in many cases, they put an X as a white space. So if you remove that, then it's easier to understand. And the next thing is they put a Q wherever you have in German a CH. CH is a combination in German that you have very often. For example, Dach is the German word for roof, and you have that CH. We have that very, very often, just as in China. Yeah? And they replaced CH or CK with a Q. So and if you go over that again and again and again, then it looks like that. There were 2 messages that belong together that I translate now for you. And in plain text, if you try to make it a little bit more readable, now it's getting easier. You see it like this, the first part and the second part. And the Germans here, they will have a chance to understand what it's all about. But you will find out that many items are mentioned double. That was also a rule. If they name something like a village, Kurtinova is a place, a village whatsoever, they simply put it down twice. Because you have to keep in mind, at the end of the day, they made something wrong. So they had typos in their code. And to get rid of that, they were forced to repeat the most important words, right? So, and I don't want to spoil your time. This is what comes out when you read it. And I can tell you, as a German, it is really, really hard to understand. You really have to have the context. So you should keep that in mind if we now come to the latest part. I apologize if I need a few minutes longer, but I hope it's interesting. I really have to honor the people that cracked that, so forgive me if I use a few more minutes. This is the real message. Try that on your own. If you find anything that is wrong in my quote, please let me know. I'm really interested in that it works. Let me tell you one thing about Bletchley Park very fast. This is from Bletchley Park. Bletchley Park, also called Station X, is a place in the area of London. Today it is Milton Keynes, but back in those days Milton Keynes didn't exist. And they were working with the help of the Polish people on cracking the enigma. And if you're interested, maybe next year or one day in the future, we may have a talk about cracking the enigma, but I think that must be a double session or something like that. It was super secret, and there are many myths about this time that the people who worked there, in many cases, they had no clue what they're working on. Only very few people really knew what Bletchley Park was, and nobody knew where it was placed, just a handful of people. And when the World War started, when the World War ended, when the World War started, Bletchley Park was invented. When the World War II ended in 1945, the British government made a very strange decision. They told their employees that were back in those days up to 10,000 people. Almost everyone working there was a woman, because the men were forced to work in the army on fighting the Nazi Reich. And they told him, you must not talk about that. For 30 years. Gordon Welchman, one of the notable guys who cracked the enigma in the team of Alan Turing, he was an expert. He went to the United States, and in the early 80s, he was so fed up with that he wrote a book and told the public what happened in World War II. Because you have to think about that, the people have, in the eyes of the public, from the view of the public, those people working in Bletchley Park, they were not soldiers because they were not really fighting. You know what I mean? So he wanted to give them credit that they ended the war. From our perspective today, you never know, but many people say the World War II would have lasted for 4 more years, 5 more years without the work of Bletchley Park. So that is the reason why I'm very interested in that, because it is obvious that Germany had to face nuclear bombs without Bletchley Park. So I'm pretty thankful. It sounds a little bit weird, but I'm pretty thankful that the war ended in 1945 and not in the 1950s. Yeah? Something like that. They wanted to screw the whole area up, and then Bletchley Park Trust was established in 1992. I think it is very strange. But to make it even more special, this is the office of Alan Turing, and that's a real tragedy, because if you think about Alan Turing is such a notable scientist, and almost no one recognized what his contribution was to end the war. We do now know that today. But he actually was killed by his own government. It is not very clear if he committed suicide or if they really if they killed him. But somehow he died in a very young age, and everything that he did, he was simply gay. That's all he did. And the interesting thing is that it took until the year 2014 that the Queen took the chance to pardon those people who were sentenced to jail treated like that simply because they were gay. And it took until 2017, that is the second year of the PowerShell conference, since homosexuality in Great Britain wasn't even longer a crime. It's interesting, right? But I also think we must not forget the progress that we made, we as a society. I don't think that we are today on such a strange place, but it's amazing that it took so long, right? This is a memorial for the Polish people, because if you visit Bletchley Park, I highly recommend that. You learn how important the Polish scientists were. And this is the memorial over there. And my final thing is, he died in a long, long time ago. What would be the situation today if people like Alan Turing would have lived for decades longer? If they wouldn't have to keep all that secret, they destroyed all the early computing machines. Yeah? Where would the United Kingdom be today if they were open-minded, if they invest in that computing science? They didn't. It's interesting, right? And he really is an amazing guy, because that is exactly what I think when I use ChatGPT today or any stuff like that, right? That's it. I told you about my motivation was to understand Python and PowerShell, and my final slide, this is Python and PowerShell compared. You see it is well comparable, right? Another example, the same code, Python, PowerShell, and that was the reason why I made it, but I really encourage you to read a little bit about that. It's a very, very interesting topic. Visit Bletchley Park. You can now because of the trust, and read about it. I think it's a very, very interesting topic. So this is Bletchley Park, where I was. So I apologize for taking a little bit more time, and feel free to ask questions if you're still awake. Thank you.